Hello everyone, I am Pragya Srivastava. I am here to record a lecture on VLSI technology. The course code is KEC053. Today I am here to record a lecture on its unit 3, which is film deposition. Previously we have seen how the lithography and etching is carried on. In this slide we see that deposition, which is we are going to study deposition. Deposition, we have various methods, but presently we are going to study chemical vapor deposition. Other than chemical vapor deposition, we have physical vapor deposition, we have sputtering, we have electroplating, so there we have different methods, but presently we are going to discuss chemical vapor deposition. CVD, which is chemical vapor deposition, involves dissociation and chemical reaction of gases reactants in an activated environment, followed by formation of stable solid product. What is happening is, activated environment means either in presence of heat or in presence of light or in presence of plasma. It can be pressure, it can be in presence of high pressure, it can be in presence of high temperature. Also, it can happen in condition of low pressure, but also high temperature, like in case of plasma. Some materials are there where we have high melting point. In that case, we have to go for a higher temperature, but at the same time, we maintain the low pressure condition. So, the formation of soot, it is a layman example. Formation of soot due to incomplete oxidation of firewood since prehistoric times is probably the oldest example of chemical vapor deposition. So, we have seen the formation of soot in prehistoric times, where the black soot comes out due to incomplete combustion or incomplete oxidation. So, that particular feature is nothing but chemical vapor deposition. What is chemical vapor deposition? A process where a solid material is deposited from a vapor by chemical reactions. So, we are trying to incorporate, we are trying to accommodate more number of chemicals. Let's see an example of a picture where we are showing the Cvd reactor. So, it is a chamber. Here we are combining 2 or more gases, and these 2 or more gases will result into a third gas, which will solidify, and it will get on the surface of settled on the surface of wafer. So, here we are talking solid material is deposited on the wafer. So, how that on the wafer, and how that solid material is created? It is created with the help of chemical reaction, which is being conducted in vapor form in the vicinity of the substrate. The solid material is obtained by coating, powder, or a single crystal by varying experimental conditions. So, what can be the experimental conditions? We can increase the pressure, we can increase the temperature, we can add some catalyst, a new gaseous mixture, or we can change any property. So, using these environmental conditions, we can achieve the formation of particular metal which we want to deposit. So, it is a solid vapor reaction. Reaction takes place in gaseous form, that is vapor, is converted into solid form, which is nothing but the material, which is nothing but the material which is to be deposited, which is to be deposited. So, this is a basic study behind chemical vapor deposition. The main components of chemical vapor deposition equipments is chemical vapor precursor system, and then the role of component is to generate vapor precursors and to deliver it to the reactor. To provide or to make these gases enter the reactor. The design of CVD reactor depends on whether the starting material is solid or liquid. So we can see that this reactor cannot work for liquid. This can only work for solid reactor. Sublimation of solid precursors depends upon surface area of solid and contact time. The liquid sources often use a bubbler. So this reactor which we have seen is not for liquid, it is only for gas. For liquid we have bubbler, okay, to vaporize the reactant, carrier gases, and to transport the vaporized reactant into the reactor. Now what is happening here is, we have two kinds. One is the hot wall reactor and the other is cold wall reactor. So cold wall and hot wall, it all depends that this is a reactor. Here we have, what is happening here, we have certain heaters here. So when the presence of heater will increase the temperature of the wafer. So when this increased temperature is only within the chamber, not around the walls. So walls of the chamber are cool. So that is called cold wall reactor. So another case, the substrate and the walls of reactor are heated up. So it is called hot wall. And the example of this is disadvantage is contamination. Disadvantage here is non-uniform layer of the film. So depending upon the parameter which we decide, we can choose either of them. The effluent gas system, the component consists of neutralizing part for the exhaust gases and vacuum system to provide required reduced pressure. The unreacted precursors and corrosive byproducts such as HCl are neutralized by trapping these liquid nitrogen trap. Inflammable gases like hydrogen are burned off. It is a typical CVD equipment where we can say the substrate is exposed to one or more volatile precursors which react and decompose on the substrate surface to produce the desired deposit. So during this process, volatile byproducts are also produced, which are expelled out of the system, removed out of the system through a reaction chamber. So we can see here that this is a chamber here where we are actually keeping the wafers, and this is the pressurized or compressed gas. So depending upon the inlet valve which are placed here, a controlled amount of gas will enter. So a controlled amount of gas enters here, and here we have a wafer handling system. So this wafer handling system will expose the wafer to this gas. Of course, those gases will react, and the byproduct or the gases which are produced and not needed will be expelled out of the system. So this is a typical CVD equipment. Now we have to study the molecular level physics behind this deposition process. So first we will see this mechanism. What is happening here is the main gas flow or the parent gas is entering. Here we are showing it with the help of green bubble. So this gas phase reaction, when like A and B reacts, the component C is very much suitable to get adsorbed on the surface. So let's say this is A, or this can be B as well. So A or B, any of them. After combination, the most suitable molecule is C. So this C is to be adsorbed. So here we can see it is adsorbed on the surface. So once it is absorbed, it can remain and it can settle permanently. In case it does not settle and it still has sufficient energy that it moves out of the system, it is again dissolved as a precursor. It can come again, try and deposit again, adsorb again. So in case the molecule does not get sticks to the surface of the wafer, it can go again back to the system and come again for deposition. Let us consider another case when the molecule has successfully adsorbed the surface. So we can see the color has changed from red to orange. So this orange color shows that it has deposited. Now once it has once it is deposited, the deposition process is complete. It changes its color to red. Sometimes even after absorption has completely taken place, deposition has completely taken place, some of the volatile products move out of the system, and now this is a byproduct. So this byproduct is no more needed, and desorption of volatile surface of reaction products, so they have to move out of the system. Okay. Now this process of adhering to the surface of the wafer is called step coverage, or it is also shown here as step growth. We call it step coverage. We call it step coverage. So step coverage is nothing but the throughput or the speed of output. We are going to study it in detail, starting from here. Transport of reactants into the region. So all the gases are entering. Transport of reactants from the main gas stream to the substrate. Now they are entering to the substrate area. After they are entering the substrate area, adsorption. We want this molecule to get adsorbed on the surface. The chemical decomposition and other surface reaction takes place. Desorption of byproducts from the surface. So once it may happen that adsorbed a molecule gets dissolved, so it moves out of the system, out. Transport of this already out of the system byproducts to a place which is outside the chamber. Transport of byproducts by forced convection away from the deposition region. So this is a step-by-step flow chart and defining the mechanism behind CVD, chemical vapor deposition. Here we have different types of CVD. We have low pressure chemical vapor deposition. We have metal organic chemical vapor deposition. We have photon induced chemical vapor deposition. We have plasma enhanced chemical vapor deposition, and when we have atmospheric pressure chemical vapor deposition. See, all these 5 are different types of CVD, but all will have certain advantages and disadvantages. So we have to study the basic physics. Like, let's say we talk about laser induced chemical vapor deposition. Here the molecules, means we are not providing any heat. The molecules combine and stick on the surface of wafer, and this process is facilitated with the help of laser beam. So we have a laser beam here, and then we'll be having some, of course, advantage and disadvantage. Another, like plasma enhanced. Plasma enhanced means somewhere we have metals which we need to deposit, but the temperature is, the melting point is very high. So sometimes when the melting point is very high, we can only do this using a plasma enhanced. So again, there will be some advantage, some disadvantage. So we will be studying each one of them very quickly, very briefly we'll discuss. Atmospheric pressure chemical vapor deposition. So it works at atmospheric pressure. It is used to deposit a layer of material, typically several micrometer thick, onto a wafer. So when the thickness, when the thickness is the constraint and we need to deposit, we will go for atmospheric pressure. It is used as a surface finishing process for items such as tools, turbines, blades to improve lifetime and performance. So vacuum system is not required here, and APCD system is low cost. So this is the advantage here. Inherently poor utilization. So this is disadvantage. Extremely susceptible to oxidation due to greater gas density and residence time. So these are the features. Next is low pressure chemical vapor deposition. So low pressure chemical vapor deposition, it has excellent uniformity. So uniformity is high, means the layer which is deposited is very much uniform. High purity, good step coverage. So step coverage we have studied what is. We can see this one is the step coverage. It works at subatmospheric pressure. Reduced pressure tend to reduce unwanted gas phase reaction, improves film uniformity across the wafer. The low pressure increases the precursor diffusion through the gas, and the mass transfer rate of the gaseous reactants become higher than the surface reaction rate. So exactly what pressure we need to know. So it is around 10 to 1000 pascals, and the standard atmospheric pressure is 101,325 pascal. Next is metal organic. Metal organic, why we are using metal organic compounds? So we have to see when metal organic compounds are used as molecular precursor to deposit a wide variety of thin film materials for new industry application. Let's say we are very specific. We have certain industrial application. In that case, we can only take those metal organic compounds. The great advantage of MOCVD precursor is high temperature, high volatility, moderate low temperature, and therefore the reaction temperature is around 750 to 1100 Kelvin at then conventional CVD. So here we have certain disadvantage. That disadvantage is that it is very expensive and very volatile. So when the reactive liquids are used, they require accurate pressure control to purify. Next, we have seen the chemical laser enhanced chemical vapor deposition. Let's say here we have a wafer, and then we have certain molecules, gaseous molecules in the picture. On the top of this, we expose the system to laser beam. With the help of this laser beam, these precursor molecules will come and settle. We have seen that here we can see that the molecules are settling, and this byproduct is there which will move out of the system. Chemical laser enhanced chemical vapor deposition uses a focused laser beam to heat the substrate. It also has the ability to locally heat a part of substrate while passing the reactant gas, thereby inducing film deposition by locally driving the chemical vapor deposition reaction at the surface. It is used to deposit micro-scale solid patterns or three-dimensional structures on the surface of the substrate by localized single-step coverage. Next is plasma enhanced. Plasma enhanced CVD, we have to see that sometimes it happens that we have a certain family like SiO2, Si3N4, SiXNY, SiXOYNZ, and amorphous silicon films. So plasma can be used to decompose a molecule that will not decompose at a reasonable elevated temperature. So even if the temperature is very high and the molecule is not decomposing, so in that case we have to go for plasma enhanced. So it is used to decompose a thermally unstable molecule but at a much lower temperature rate. The plasma CVD substrates that cannot tolerate high temperature, such as polymers, can be used where substrate temperature ranges between this. So we cannot use high temperature because that polymer or that material won't be able to withstand that high temperature. So it will not decompose the way we want it to be. So they are thermally unstable molecules at high temperature. So we have to go through plasma enhanced. Advantage: chemical vapor deposition films are generally quite conformal. The ability of film to uniformly coat a topographically complex substrate. Next is versatile. Any element or compound can be deposited, and they have high purity. High purity can be obtained. High density, nearly 100% of theoretical value. CVD films are harder than similar material produced using conventional ceramic fabrication process. Material formation well below the melting point. So well below the melting point means we can deposit the metal at a substantially lower temperature, which is not even the melting point, and economically in production since many parts can be coated at the same time. Here is the disadvantage: chemical and safety hazards caused by the use of toxic, corrosive or flammable explosive precursor. So they are the safety hazards. Therefore, extra steps have to be taken to handle these precursors and in the treatment of reactor exhaust. High deposition temperature, generally which is more than 600 degrees Celsius, are often unsuitable for structures already fabricated on substrates. So we have already fabricated material on the substrate. So 600 is already harming that thing. Restrictions on the kind of substrate that can be coated. It leads to stress of film deposited on materials with different thermal expansion coefficients. So which can cause mechanical instabilities to the deposited films. Next, we have application, like once we need to do coating, and coating of various variety of application: resistance, corrosive resistance, high temperature protection. Then we have semiconductor related devices like IC, sensor, so optoelectronic devices. In fiber optics, we use in telecommunication, used in microelectronic industry to make film serving as dielectric conductors, passivation layers, oxidation barriers, buried layers, and epitaxial layers. That was all about chemical vapor deposition. We'll be studying more like physical vapor deposition in my next class. Thank you.